Hey, folks. So, we now finished kind of the first set of the course, the first kind of unit, which was dynamic programming and recursion. All right, and so we spent the first, say, 4 weeks on that, thereabouts. And now what we're going to pick up on is Markov chains. And what they are is like the dynamic programming, where we had a state and we're moving through the future states. Markov chains are similar, right? Where there's certain states and you're moving between the states. What makes it interesting is that, first of all, with just standard Markov chains, there's no decision making. This is more like with the Fibonacci, where you were just forced through it, and there was no decisions to be made, which is what we had in dynamic programming. Here, there's no decisions, but you don't just go to one state. Instead, what's going to happen is there are multiple different states that you can go to, and it's just random chance on which ones you go to. And so what we're going to do is we're going to spend a couple weeks analyzing those, probably about 2 weeks. And then what we'll do is we'll spend a week tying them in with dynamic programming. So what do you do in a dynamic programming environment where you get to make decisions, but based on your decisions, there's different probability of going to different states. All right. So that's what we're going to be doing from here on for the next few weeks. All right. After this, just as a quick little heads up, in case you've forgotten, after this, we're going to be moving on to, so this is stochastic shifting of states. And then we'll finally move into the last section, which will be uncertain states, which will be where you don't know which state you're even in. And you have to try to figure out what state you're in. And so we'll analyze first how to do that using Bayesian inference. And then we'll tie in some Markov chains with it, which will be hidden Markov models. And then finally, at the very end, we'll tie it all together. All right. And that'll be partially observed Markov decision processes. So it should be pretty fun to see as we start tying all three of these things together. In case Bayesian inference. All right. So it should be a lot of fun. I think we're going to have a lot of fun. You'll learn a lot for each one individually, and then also how they interplay with one another. All right. So let's get on to Markov chains. So this is going to be a fairly short lecture. And the reason why is, well, both this one and the next one are. All right, they're both going to be probably maybe only like a half an hour, 40 minutes is my guess. You can look down at the bottom of the YouTube clip and we'll see if I was right. But I have no idea. We'll see. I'm planning on it being not too long. But the reason why is because in between the two lectures, there is essentially, today we're just going to focus on doing everything on the computer pretty much. And next week, we're going to go back and do some of the analytical solutions. So we actually have to solve some of the further properties and derive some results. And to do that, we need linear algebra. Now, it used to be in past years, I would put together this full lecture all on linear algebra, talking about how you can view them as linear transformations, finding the determinant, finding the eigenvectors and eigenvalues. It was a lot of fun. I loved teaching it. And it was mainly because I felt like most people didn't get a good intuitive feel for linear algebra whenever they learned them, if you ever did. But then one year, this was like a year or two ago, I was teaching it all, and then somebody came back to me and said, "Oh, you teach it just like 3 blue, 1 brown does." And I was like, "Teach it like what?" I had no idea what it even was. So they sent me a link, and I watched it, and it's this mathematician who I guess has a pretty big following and stuff on YouTube, has millions of views. And he goes through all of linear algebra, and by golly, he teaches it just like me, except with one difference. He teaches it much better. So he has like all these really cool animations, right? And they're really cool looking animations. He has a much better voice than me. So, and he just also covers even more topics because, it can be, he has like 16 10-minute lectures. You only need to watch like 4. So what I'm going to do though is instead of me going through it all on the board with just the whiteboard and drawing pictures and arrows, you can just watch the 4 lectures from this guy. They should be linked underneath. So you don't have to watch them right now, but watch them before my next lecture. So you have at least like a week or 2 to watch. All right, there's just 4 of them. They're about 40 minutes in total. So you can just do that as well. All right, now that I've already wasted the first like 5 minutes of my 30 or 40 minute lecture, I should probably get going. So let's suppose we have a world where we want to do weather prediction. There's a very straightforward, simple problem. And our model is going to be just dead simple. What it says is this. If the probability that it's going to be sunny tomorrow sunny. I don't know why I use my finger to erase. I have an eraser. All right. I don't know how to spell tomorrow, do I? Oh dear. Oh no. No. That's definitely wrong. It's 2 F's, right? Okay. Just one of those days where uh things starts looking weird. Do you know what? I got a better solution. All right. X n plus 1. Given that it's sunny today, there we go. Just don't even write it. All right. So what we can do is we can say something like this. What this says is that the probability that tomorrow is sunny, day n plus 1, given that today is sunny, right, is equal to 0.9. And maybe I'll even write this a little bit more explicitly for you guys. Let's write it like this. Equals sunny, given xn is equal to sunny, is equal to 90%. What that says, this is like a pretty good model for around here. If today's sunny, there's a 90% chance tomorrow is going to be sunny. That easy. And then we can say probability that tomorrow is sunny, given that today is, let's say, rainy. So in this world, and we'll say that's 50%. So in this world, there's only 2 states of the world. Either it's raining or it's sunny. It's either rainy or sunny. And if it's sunny today, then tomorrow there's a 90% chance it's going to remain sunny, and a 10% chance implied here that it becomes rainy. Meanwhile, if today is currently rainy, it's a 50-50 chance on it either staying rainy or becoming sunny. That's our entire model. So let's analyze it some, shall we? So first things first, suppose today is sunny. All right. What's the probability tomorrow is sunny? P of x. So we'll say today, and we'll label this x1, let's say. We also label it x0. Let's label it x0 because we're now programming. This is computational economics. So everything starts at 0 for us. All right. So x0 is sunny. All right. X0 equals sunny. So now, what's the probability x1 is sunny? All right. Given that x0 is sunny. Well, that's easy enough. Why, we already said right here. If today is sunny, then tomorrow there's a 90% chance of it being sunny. And therefore, what's the probability of it being rainy? Well, it's 1 minus that. Therefore, probability that x1 is rainy, given our x0, sunny, that has to be 0.1. Easy. What about 2 days? What's the probability 2 days from now is sunny? Probability sunny in 2 days. Stop right here. Try doing it on your own for a few minutes. All right. And then once you're done, you can just resume. I'll pause right here. Okay, let's go. So let's run through it. What we want to know is probability that x2 is sunny, given that x1 is sunny. All right. Well, I'm sorry, not x1, x0. All right, we want to know in 2 days from now, right? All we know is today is sunny. We want to know in 2 days. So how do we do that? Well, what we can do is first we can use these results if we wanted, right? There's a 90% chance that it's sunny on right here, right? Tomorrow. And so we could say, okay, well, 90% of the time that it's sunny tomorrow, it's going to stay sunny the day after. So it's going to be 0.9 times 0.9, which will give us 0.81. But then we also have to account for the fact that if tomorrow is raining, that there's still a 50% chance that after being rainy tomorrow, it's going to become sunny again. So that's going to add a 0.05 on top of that. So we should get 86% chance. That's what our intuition already says. So let's actually try to do this systematically. All right. So what we can do is we can say in general that the probability that it's sunny in 2 days and that it's sunny in so the trick on doing this, you can do it a lot of different ways. I'm going to write it out kind of just a simple mathematical way, and then we'll show how it simplifies. Plus, all right, so this is actually a fairly straightforward equation, even though it looks a little bit weird. What's happening here is that the sum of these two have to be equal to this. And the reason why is first, just ignore this conditional statement. All right. The best way to view it is just by ignoring this. What it is something like this. Suppose I asked you, um, what's the probability of, doesn't really matter what we want to talk about here, but let's just say, what's the probability that I roll a die and it comes up 1, right? A die is equal, that it rolls 1. Well, what we can do is we can also say, well, okay, you know, hypothetically speaking, this should be equal to the probability that the die that I roll, suppose I roll a die and I flip a coin, for example, right? It could be that it's the probability that I roll the die after I flip a heads, plus the probability that the die I roll equals 1 after and I flip tails. Right? So the idea is this, right? You can imagine I flip a coin, roll a die, right? I can get a 1 and a heads. Here's the die roll. Here is the coin flip. Oops. There's only 2 possibilities for the coin flip. So you can either get 1, 2, 3, 4, 5, or 6, or you can have heads or tails, right? And so if I'm asking you here, what's the probability of a 1 in all? Well, that's the probability that I get a 1 and I get heads, plus the probability that I get 1 and I flip tails, right? So in total here, x1 can only be sunny or rainy, and then the probability of being sunny has to be the sum of these two events happening, right? We can write down, x1, x2, x1, and then sunny, rainy, sunny, rainy, and we are interested in when x2 is sunny, so that's the sum of these two. This is the formal way to do it. All right. doing it very formally. Like I said, in your head, you already know the answer, but we're going to do it this way. And then the only question is, okay, how do we do this? Well, this one we can use the rule of conditional probability. For a probability of, and by the way, if you guys are a little bit confused with this probability stuff, don't worry too much. In 2 weeks, when we get to Bayesian inference, we're going to redo pretty much we'll build up all of probability again for you. All right. But for right now, just go with your intuition and you can ignore this math if you so please. All right. So that one is going to be equal to probability of x2 equals sunny, given x1 is sunny, and also x0 is sunny, times the probability. Ooh, I don't have enough space here. Let me erase and do it on the other side. So this will be probability that x2 is sunny, given x1 is sunny, and x0 is sunny, times the probability that x1 is sunny, given that x0 is sunny. So we have that, and then we still have to do the second one here, right? So now all I'm doing is taking this right here. This little equation right here has become this guy. All right. It just expands out to that by rules of conditional probability, which, by the way, in case you don't know, is just that probability of A and B happening is equal to the probability that A happens given B happens times probability of B. Right. And then also, of course, you can reverse the A and B, and that's fine too. All right. And so here, what you're seeing here is that the probability that x2 and x1 are sunny given x0, all I've done is just taken this part right here, x2 and x1 becomes x2 given x1 times the probability of x1. And then because this thing is conditioned on x0, both of these are also conditioned on x0. And that's all it is. So it just expanded out a little bit messy, but that's okay. It would have been much cleaner if I had just not had to write sunny after everything. Right? And then we just have to add on the other one, which is x2 equals sunny, given x1 is rainy, x0 is sunny. This is the real messy expansion of it all. x1 equals rainy. Usually, you would just kind of skip a few of these steps and do it kind of implicitly. But I wanted to make sure you actually saw all the nitty gritty here. So, this is the key thing. All right, we're about to get to the most important thing, which is right here. This right here is the key assumption to all Markov decision process or Markov processes, Markov chains. This is what makes it a Markov chain of first order, which is that we said that the probability for it tomorrow, given some fact about today, I think I wanted x plus 1, given is equal to some value, right? That's what we had set, whatever this value is, right? And the key thing about this is that knowing what it is, if I want to figure out what it's going to be tomorrow, all it depends on is today. It doesn't depend on what yesterday was. All right. If it was rainy yesterday, sunny today, there's a 90% chance it's sunny tomorrow. If it was sunny yesterday, sunny today, still a 90% chance of sunny tomorrow. All that matters is that it's sunny today. The previous week doesn't matter at all in our prediction. That's what makes this a Markov chain, and specifically a first order Markov chain, which means that it only depends on the previous state, the previous one state. A second order Markov chain would rely on the previous two states. So that would mean that if it was rainy, sunny, that would give some probability that tomorrow is sunny. Or if it was sunny yesterday, sunny today, that would give a different probability. All right. But because it's a Markov chain of first order, this information is unnecessary. It's superfluous. Doesn't change our probability. So we can just erase it. Does not matter. All right. And now we can evaluate this. So let's see here. First of all, what's the probability that it is sunny tomorrow, given that today was sunny? We already said that's 90%. So now we can start filling this in. So this guy is, let's see, we got the 0.9 right there. And then what's the probability that it was rainy? That was 0.1. That's something we already had. And now we got to evaluate these. If tomorrow is sunny, what's the probability that the following day is sunny? 90% plus. And then if it was sunny, if it was rainy tomorrow, what's the probability that it will be sunny the day after? 50%. All right, that's the long, tedious way to finally get this 0.81 plus 0.05, which equals our 86%. Just like I had said to begin with. And now if we want to get the probability of rainy in 2 days, well, we can do this whole thing again. Of course, we can skip a little bit to quickly get there, but we also know it's just going to be 1 minus this, right? So sunny in 2 days, and then rainy in 2 days. All right, that was tedious math, but easy enough, right? We can easily do it. When we do it for 3 days, all we have to do is now just, now unfortunately with 3 days, there's a lot of different chain, right? It could go like sunny today, and then it could go rainy, rainy, sunny. It could go sunny, 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 rainy, sunny, sunny, rainy, sunny, sunny, right? There's like 4 different probabilities. It keeps like kind of 4 different ways, so it keeps branching out. So the question is, though, can we figure out how to do it, right? Well, first of all, we're a little bit lucky here, which is that if I know that the probability is rainy and sunny in 2 days, in 3 days, I can just use that to figure it out, right? Because now that we know this, what is it in 3 days? Let me just actually quickly do this. Only this time the math will be, I'm going to shorten it, right? 3 equals sunny, given that today is sunny. Well, that's easy enough. We can just split this up. We just like we did up there, where it's going to be probability that it's sunny in 3 days, given that it was sunny in 2 days. X2 is sunny times the probability. Once again, only because of the first order Markov conditions that we had there, times the probability that X2 is sunny, given X0 is sunny. Right, so now what all this says is that, and then the same thing, we have to add on the same thing, but with rainy. Right? And so this is really easy. This just says, okay, we take these and we just apply 1 more day forward, right? So now it's going to be the 0.9 times, now what's the odds that it's actually sunny in 2 days? 0.86 plus now this one, which is 0.5 times, what's the probability that's rainy in 2 days? 0.14, right? So we can just do that again, and then we'll get it for 3 days. Now, what about for infinite number of days, right? What's it do after, say 1,000 days? Do you think it keeps fluctuating? Does it converge to a certain value? What's it doing? Does it go towards 1? Does it go towards 50-50 maybe? All right, maybe it just goes towards 50-50 because you might say, well, look, if I can't, this is a random thing after a long time. Surely you can't really say much about it. Let's find out. Let's do it on the computer real fast. All right. Let me see here. Oh man, I'm already at 24 minutes. Brutal. Sorry for going over. Don't worry, I think I'll be done actually in around 15. We just have 2 small things to do. So what we're going to do is quickly just write down prob sunny equals 1.0 today. right? I believe you guys can all see this. And then the prob rainy is equal to 0, right? So that's today, all right? So what we'll do is first things first, we'll print out the current state, which is prob sunny, or at least the current probability of being in each state. And then what we need to do is we're going to do a for loop where we'll do it for, let's say, how many days should we go for? Let's go with 20 days. All right. And then for each day, all we have to do is update it. All right. Because we're going to use the fact that if we already know the odds for today being sunny or rainy, then we can just figure out the next day by just simple math, right? So next sunny is just equal to our current probability of being sunny times 0.9 plus the probability that it's rainy today times 0.5. That's how we get the next sunny, right? And then next rainy, it's just going to be equal to prob sunny times 0.1 plus prob rainy times 0.5. And then finally, we can now update our prob sunny and prob rainy is just equal to prob sunny, next sunny, next rainy. So you have to be just a little bit careful, right? I was kind of careful with the order here. I didn't explicitly say this, but the reason why is that while we don't want to just say, okay, or now today's probability, the prob sunny is equal to this, because then you would make the mistake of using the updated value in the second line here, and that's something we don't want to do. So first I give them their own name, their own temporary names, and then I set them equal to our probability of sunny and rainy. All right. First, I'll try running this just for like 2, just to make sure it's all working. And we'll just print out the prob sunny and prob rainy. All right, let's try running this. I really should put that in a main and everything. I've been a little bit lazy with doing that. So let's see here, weather Markov. So as you can see, on day 1, of course, it's 100% chance of being sunny. And then we go through and we multiply it all, right? And then we print out the probability, and it's 0.9 and 0.1. And then we do it a second time. So now we are at 0.9.1. We multiply again, and now we're at 0.86.14. Cool. Right? And presumably, let me make sure. Oh, no, we didn't actually calculate it for day 3. So let's run it for 20 days, and let's see what happens. Last chance to place any bets. All right. Let's see here. It does appear to be converging, right? And because by the time we get down here, you can see it's like 8 with a bunch of 3s afterwards, which should clue you into 5/6. And then right here, we get 1 with a bunch of 6s, so that's 1/6. So it looks like if we run it forever, we end up at eventually getting towards 5/6 of the time it's sunny, 1/6 of the time it's rainy. So one of the big goals that we're going to be doing next week is how to derive this a lot of ways. Now, I will quickly at the end of today mathematically get this. But before we go on, I want to show you how you typically write a Markov chain, because what we're going to use is matrices. All right. So let's go back here and show how to make this code a little bit simpler. All right. Now, I don't know if you guys know how to multiply matrices. Presumably you do. But just to play it safe, I'll quickly do a quick teaching of it. I'll show you the little trick for doing it. So you've probably all seen a matrix at least. You may not know what to do with it, but you've seen a matrix. So let's suppose that you have a matrix A, B, C, D, and a second matrix E, F, G, H. And the idea is that you want to multiply these two matrices together. The way to do it, I'll show you the little trick that actually my grandfather taught it to me several years back. It's very straightforward. All that you do is you move the second matrix up above. E, F, G, H. All right. And then you draw your new matrix. All right. Got to make it be a little bit wider. Actually, I'm not even going to put the right-hand side because I'm going to need extra space. And then what you do is you just visually kind of line them up. So if you want to know what is going to be right here in this box, what you do is you just visually line it up. All right. And what you're going to get is you get A times E plus B times G. Right? AE plus BG. All right. To get the second one over, now you have to line up once again, line up the same row, and you have to line up the column of the second one. So this is going to be AF plus BH. And now when we go down here, we got to line up row with column, and we get CE plus DG. And then finally, last but not least, CF plus DH. Now, why do we talk about multiplying matrices? Because it turns out that we can condense things a little bit with our matrix, with our Markov chain. All right? And the way we do it is, by the way, it's very nice being able to just, since there's a recording on YouTube, I can just erase whenever I want, because you guys can always just back up and pause if you want to take notes. So it's great. I always was worried before, like erasing and suddenly someone would go, oh, no, not yet. Anyway, so so before we said, okay, the probability of, we can do something like this. Suppose that today has a 90% chance of currently being sunny, and let's say, oh, actually, let me do day 2 just for the sake of argument. No, I'll stick with, yeah, this is fine. Let's say this is the current state that we're in. What we want to have is, if we have the matrix, it turns out we got to write a little bit carefully here. If we have this matrix, which I'll explain in a moment, and we multiply them together, and we treat this thing as today's current probability of being rainy and sunny, right? In fact, maybe I'll even do it this way. We'll just say this thing's like P sunny, P rainy. Now let's multiply these two together and see what we get, right? So we got to move this guy up above. P sunny, P rainy. And now we got to do this multiplication, right? So we get 0.9 times P sunny plus 0.5 P rainy. And then we have 0.1 P sunny plus 0.5 P rainy. And guess what? These guys are exactly the probability of sunny if we in n plus 1, and probability of rainy n plus 1, right? When you think about it, right? If, let's say, if there's some certain probability that we're currently sunny versus rainy, then there's a 90% chance we stay sunny, and there's a 50% chance we go from rainy to sunny. And then similarly, there's a 10% chance we go from sunny to rainy. And then plus the 50% chance that we were rainy and we stayed rainy. So this ends up being the new probability of rainy, new probability of sunny, just with the simple matrix multiplication. Now, this is not, now the thing that's a little bit annoying about this, though, is that it's not how we usually might think about it, which is that we might have something like today, tomorrow. Oh boy. Nope, I've already committed myself to not writing down the word tomorrow at all, anytime today. And so, um, this is how you know I'm only doing this in one take, because I would have definitely just played it safe and gone through it, all right? And looked it up and made sure that I could spell the word tomorrow. So let's say sunny, rainy. We might want to sit there and write this as, okay, there's a 90% chance, 10% chance that it goes from sunny to rainy, and then 0.5, 0.5. This is typically the way we would draw a table like this. And unfortunately, the matrix isn't quite that. Hey, this is the natural way to make a table. Unfortunately, the table doesn't quite translate to the matrix there. It turns out the matrix is transpose of this, where what you do is you have to take along the diagonal and flip it, right? And what's nice about this, by the way, is that the rows sum up to 1. Here with this matrix, the columns sum up to 1. But, it's okay. You can do it this way, but typically what people do, we're kind of fortunate here, that if you have A times B for matrices, that is equal to B transpose A transpose transposed. Right? You can transpose a bunch of matrices to get it back around. So what the upshot is, if you don't know your matrices, don't worry about it. The upshot is that if we want to be able to write a matrix like this, which is more typical for Markov chains, you write it like this. You say, okay, here's my matrix. But now, instead of having this column vector, what we have to do is on the other side of it multiply by the row vector of it. And here, now it does the same thing where we just elevate it up and you multiply and you'll see you're going to get the exact same thing. 0.9 sunny, plus 0.5 rainy, 0.1 sunny, 0.5 rainy, and you add them up. And then you have the two out of it, right? So this should get you your P sunny tomorrow, P rainy tomorrow. All right. So just real fast, this is the last thing. I'm going to, actually, second last thing. I'm going to quickly write this in Python using Numpy, because luckily Numpy allows us to quickly do this. So let's see here. Let me go to, I'm just going to go right underneath and do it, all right? So what we can do is we can import Numpy as MP. I don't remember if I've even, whoa, Numpy as MP. That was weird. I don't know if we've talked about NumPy much. I'm sure you used it in the last class at least once. It's for being able to do matrix operations and the like. Exactly. So it lets you act on arrays or vectors or lists of things to multiply them all by a certain value or do operations on them. And it has matrix multiplication built in. So what we do now is we just have to create a NumPy array, which is going to be our current state. So our initial state is that we're sunny, 100% chance sunny, 0% rainy. And then we have to make our transition matrix, or Markov transition matrix is what it's called, which helps us transition from today to tomorrow. And that one is a matrix of 0 0.9, 0.1, and 0.5, 0.5. Right? So it's just the table we wrote. In fact, if you even wanted to, you could write it on top of each other like this. And then we can print them out if we like. Transition matrix. And print out the props. And then we can do the for I in range of 20. And by the way, that's bad format of me to be using I there when we don't actually use I ever. There we go. If you put the underscore there, it's just as if it says that you aren't actually using that value. And all we gotta do is say probs equals probs times transition matrix, right? Because now we're gonna take this row vector multiplied by the matrix, and we can print out the probs. All right, and now we can run this, and you'll see, hopefully, let me see just in case I'll move it over here. We're gonna get the exact same answer: 10, 0.9.1, 0.86, 0.14, and then so on and so forth. But it's much cleaner, right? Because it's just that one line of that matrix multiplication. And knowing that it's matrix multiplication gives us some stuff, all right? So give me just 1 second here, and then we'll finally be done. I promise. Let's see here. What am I at? 39. So I have, okay, 1 minute. So there's two things that we're interested in. One is, what's the probability on any given day? And to do that, what we're going to have to be able to do is, it's actually pretty straightforward. If we have, say, if this is 0, right, then we agree that this will be on day 1, right? If we multiply it, then we get day 1. If we want to get day 2, right, well, all that is PS of 2, PR of 2, is just equal to P1S, P1R times this matrix, right? All we have to do is multiply by the matrix again. But since we know this guy is right here, this is also the same thing as PS0, PR0 times the matrix twice. Right? You can imagine I'm going to put this in parentheses and then multiply by 0.9, 0.1, 0.5, 0.5. Right? And the reason why is that all we've done is replace this with this. And in general, right, of course, this guy is just equal to PS0, PR0 times 0.9, 0.1, 0.5, 0.5 squared. And in general, this is for PS2 and PR2. In general, if we want to get the nth value, n, PRn, what we're going to have is we just take this guy and we have to multiply by the matrix n times. That's going to be something that we want to deal with. Then we could plug in as n goes to infinity, we can try to figure it out. But at the end of the day, we're going to have to figure out how to take this matrix to an arbitrary power. And to do that, we're going to need some linear algebra. All right. So just to finish, one very last thing, to be fairly quick, is we can actually solve for the special case of infinity without too much trouble. And it's by knowing that we're going to reach a steady state. Because what we know is that, let's suppose we're going to label our equilibrium P star, right? Which should be 5/6 and 1/6 is what we expect. And if we multiply it by the matrix, let's say we take it forward a day, this was 0.9, 0.1, 0.5, 0.5. What do we get? If we get to our final 5/6, 1/6, after like an infinite number of days approximately, after a long time, we run forward one day, guess what? Our probabilities are going to stay the same. Right? That's kind of the definition of an equilibrium. So because of this, what we can say is that zero, I'm just going to label these x and y just for simplicity real fast. What we're going to get is 0.5y equals x. If we were to actually multiply these two out, 0.9x, 0.5y together have to be equal to this guy, which is the same thing, right? Probability of sunny before has to be equal to probability of sunny after. That's how we're using this, because we can set these x and y's right here. And then we get the 0.1x plus 0.5y has to equal y. Now, it turns out if you try to solve this system, you can't quite, because it turns out that these are linearly dependent, right? Which is not which actually kind of they have to be, all right? There can't be a unique solution here. We're going to replace these with fractions just to be clear. So now if you move the x over, let's say we move it to the other side, what you're going to get is minus 1/10 x plus 1/2 y equals 0. And then you move the y over here and you get 1/10 x minus 1/2 y equals 0. And you see that this is just a negative of one another. So you can't quite solve it. But what you can do, in each case, what you're going to do is you multiply by 10 here, and you just get minus x plus 5y equals 0. So you're going to get 5y equals x from both of these. They both just give you that. But we have one extra constraint, actually. That's the beauty of it. We can't quite solve it here, but we also know that the probability of sunny plus the probability of rainy has to equal 1. And so now we can actually plug in and solve, right? You plug in 5y here, and you get 5y plus y equals 1, and therefore y equals 1/6, and therefore x is equal to 5/6. So there we go. We've solved the long-run probabilities on this. But what we're going to do is be able to analyze a lot more once we do some linear algebra. All right? So that's what we're going to be doing next week. And meanwhile, in class, we're just going to actually simulate a few kind of cool things, including the the game Chutes and Ladders, or Snakes and Ladders, depending on where you're from. All right, so that does it for today. I'll see you guys in class.